Okay, guys, that's sorted. I'm going to start the broadcast now.
Very good.
The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everyone. I'm Nandine Bazima with the American Biogas Council, and I'd like to welcome you all to the first webinar in ABC's Operator Webinar Series. I would like to thank our partners, Veolia, Yield Energy, and Highmark Biogas for helping to put together this event, and thank you all for joining us today. So just a few quick notes about the webinar format. There are two audio options that are available to you for this event. You can either stream the audio through your computer or dial into the event using your telephone. We will have a Q&A session following the presentation. During the event, if you'd like to submit questions for our panelists, you can do so using the question panel to the right-hand side of your screen. During the Q&A, we will then field your questions to the panelists. Also, this webinar is being recorded, and we'll send an email out to everyone with the link to the recording as well as the slides as soon as they become available. So just to briefly introduce you to the American Biogas Council, we are the overarching trade association in the U.S. that promotes the biogas and anaerobic digestion industry. We have almost 160 members that span the entire supply chain, including manufacturers, engineering firms, project developers, financiers, and many other interest groups. Some of our key industry goals are to promote biogas markets, technologies, and infrastructure, achieve policy parity with other renewables, and to promote anaerobic digestion as a best practice for environmental stewardship and greenhouse gas reduction. So we're changing the biogas industry through legislative and regulatory affairs. We lobby for and support public policy at both the federal and the state level that benefits and promotes the use of AB and biogas production, through our specialized working groups that draw on the expertise of our members to address key focus areas, and through education and outreach activities focused on building widespread awareness of biogas and its benefits through webinars such as this one, briefings, presentations, and other such means. So, on to our speakers. Our first speaker is Richard Maddox. He is Senior Technologist at Biomethane. We have Trevor Nicol, who is General Manager at Highmark Biogas, and we have Tom Ferencevich, Vice President of Technical Services at Yield Energy. And to introduce you to our first speaker, Richard Maddox. Richard has been a Senior Technical Advisor for High Solids Digestion Systems at Biomethane for the past 6 years, for the past 6 years. He has contributed to over 100 digester projects, including direct management coordination of 20 animal waste methane systems, assessing technical and financial feasibility, financing, design, review, regulatory compliance, energy and byproduct recovery, processing, and sales contract. He has provided consulting services to both public and private clients in the States and overseas, and has performed several dozen farm and centralized digestion system feasibility studies. And with that, Richard, I hand it over to you.
Very good. Mandy, were you going to advance the slide there? Very good. Thank you very much for this opportunity to discuss a topic that I think is, most of us will agree, is of immense importance to the industry. The methane potential of the substrates that we're digesting. This presentation addresses methane potential of substrates. My fellow panelists will be discussing handling and discussions regarding this often non-homogeneous material that we put in the digesters. Biomethane potential, BMP. It's far too large a topic to discuss in only 15 minutes, but I recommend just kind of sit back and listen to the presentation and then go to this, the slides once they're available. There's quite a bit of material for you. This is a quick review, folks. Slide. Next slide. There we go. The message to be conveyed in the next few moments are stakeholders need numbers to make rational decisions. The BMP test is one of several ways to know the quantity of gas that can be derived from a waste. but it's a good way, and it's also a good way to get a good budgetary estimate. Substrate quantities and qualities, as well as delivery schedules, are important to know. There's multiple BMP testing protocols out there. There's many substrate BMPs that are published, and many testing labs are available. Next slide, please. The question is, how much gas can be expected from a waste? There's many ways to measure it and to report it. You probably have heard about how much gas can you produce per digester volume, or how much gas per cow, or how much gas per pig, with disregarding whether it's a black cow, a red cow, a pastured cow, or a 70-pound pig versus a 280-pound pig. And more recently, there's we've also heard about cubic feet per gallon or truck or ton of waste, and more recently there's increasing awareness that we need to report gas production per pound total solids, pound COD, or TSS, or RVS. Next slide, please. I'm sorry, go back. Okay, so what's needed is a single meaningful metric. The biomethane potential is a useful number regardless of waste or condition. Simply put, it's the amount of methane that can be expected from a kilogram of volatile solids in a substance. So once you know the volume of waste that you're going to be processing, and through that you know what the quantity of volatile solids are that are going to be processed, you multiply that times the all-important BMP number, the methane that can be expected per pound or per unit volume of per unit mass of volatile solids, and you end up with a methane quantity. Next slide. Who needs to know the number? Who are the stakeholders? Owners, money folk, they all need to determine the financial viability of their venture. System designers need to know for purposes of design and peak energy demands. Process designers need for system and operational designs. And operators need to know in order to formulate their daily recipes. We just started up a system not too long ago that works with close to 200 different substrates and substrate dilutions. Tom actually will talk about feeding the bacteria at a rate so as not to upset them a little bit later on. Next slide. Before we start the methane yield discussion, however, we need to recognize and admit the methane yield of a substrate is meaningless in predicting total gas unless we also know what the quantities are of the substrate that's going to be processed. Next slide, please. This is a real chart of real substrate. You'll notice that there's a high substrate flow that is nearly double the low substrate flow throughout the year. The question is, that is relating to this substrate availability, is do you design for maximum flow and have stranded capital during part of the year? Or do you design for something less and you see a flare? And the all-important question that quite often is overlooked, do you have enough gas when you need the energy? Trevor's going to be talking a little bit later about feedstock supply and availability. Of course, it's a very important topic. Next slide, please. So back to the topic at hand. How much gas can be expected from a substrate? There's a variety of different ways of determining how much gas you're going to be able to produce per unit substrate. These here are all ways to derive actual values from the interaction of bacteria to the substrate. One really interesting way to find out how much gas you're producing per unit substrate is to build the system and find out. And hopefully you get what you were expecting. Another, which is a little more rational approach, often is to have a smaller pilot scale system, less expensive, and you can still generate good numbers. Bench scale systems are smaller yet, significantly less expensive, and still can generate some pretty decent numbers in terms of how much methane you can expect for the substrate. What we're going to be talking about more here as the conversation continues is the small scale lab test, the BMP test. BMP tests are small, reliable, and they're inexpensive, and they can provide you 10, 15% accurate budgetary values for gas yield of a substrate to be tested. The technique also helps you identify some potential toxicity issues. And there's also non-biology-based ways of predicting gas. You essentially do spreadsheets using some rules of thumb and perhaps some laboratory analysis and rules of thumb. Next slide, please. The BMP test determines the ultimate methane potential of a substrate. It does not permit actual design of the digester. It's a fairly simple procedure. You put a known quantity of substrate in an airtight glass vial with an appropriate quantity of seed, appropriate seed. Hold it at usually right around 198 to 100 degrees F, and you measure the volume of gas and you note the cumulative quantity of gas, and you create a curve. Next slide. But the results are only as good as the laboratory that's implementing them. Labs must adhere to acceptable protocols. There's they need to maintain good laboratory techniques, use acclimated seed, employ the proper seed feed ratios, and of course you have to back out of your results the gas that is contributed by the seed itself in your curves. Next slide. Several protocols are available. Here's a few of them. Please, I try to include a lot of references here so you can go back and find this material yourself. Next slide. You'll notice that there's an ISO standard for biomethane potential determinations, and here's an ASTM standard. Next slide. And here's the granddaddy of them all. This is a publication put out by Perry McCarty and his colleagues at Stanford in the 70s. Next slide. Before the test begins, you have to secure and analyze as representative as possible sample that you're going to be testing. And you also need to secure seed material from a digester that's successfully treating a similar type of waste. Next slide. Have a lab characterize a substrate. There's a number of different parameters that laboratories will perform, but pay particular attention to density of the substrate and the volatile solids of the substrate. Next slide. So, getting specifically into the test itself, the test is conducted in serum bottles, what's referred to as serum bottles often. What the protocols call for 160 to 200 milliliter serum bottles. All the tests that are done in triplicate. The experimental design is that you have the actual sample itself. You measure that in triplicate. You have triplicate vials of that. You have vials of the sample slightly diluted, and then also samples that are further diluted, all of which 3 vials of each. Then you have 3 vials of strictly the seed material, and then you have 3 vials that are the of an assay material, something that at ultimate that you know what the ultimate methane potential is. Acetate, cellulose, and there's others are quite often used. Procedure, which you put in the vial the substrate to be tested, a seed material, and a nutrient mix. You flush that vial with nitrogen and or carbon dioxide, and you seal the vial. You hold it for hold it at about 100 degrees for anywhere from 20 days up, depending on what the material is and how the curves look. And you agitate it periodically. You monitor the quantity of gases being produced. You monitor the quantity of methane that is being produced. There are some BMP protocols that actually scrub out the CO2, which permits you to read the methane directly. Once you have all those individual days of methane that's produced, you take the seed material and you average what the seed gas was, and you subtract that from what your test vials were. So what you do is you determine the methane production that is non-seed based. You average those triplicates and you discard any outliers, and of course you chart everything. And of course the assay test is an opportunity for you to check up on your technique. If you know what the gas should be for the assay material, you're running the test and you'll see how close you get. Next slide. One method is to just quite literally inject the syringe needle down through the septum of the vial, as you can see here, and you remove accumulated gas on a regular basis, noting the volume, of course, in the syringe, and you can also inject that gas in an analyzer. An alternative method is to use actually put pressure transducers in the septum of the bottle and through some math determine how much gas is produced on a daily basis. And yet there's other ways to monitor on just continually monitor and digitally record the gases being produced. Next slide. Here's another technique. We actually do this quite a bit here at Biothane, these larger bench scale units, 2, 3, 5 liter units that it's the same concept, but it's just larger. Next slide. So what you do then is you take the gas volumes that are determined periodically and you plot out the cumulative quantity of gas. What you're looking for is the point at which the gas production levels off. That's your ultimate methane yield. Here's some older charts. You'll notice here on the y-axis is cumulative methane yield, quantity of methane per kg VS added. On the y-axis, the x-axis is over a period of time. You'll notice these are some really recalcitrant. Several of these are rather recalcitrant materials, so they let them run out for several. All the way out to 90 days. You also note here that I've cited a number of different papers. Go there to learn more. Next page. Next slide. Here's another test, shorter periods of time. You'll note here, though, that this is reported in biogas yield on the y-axis over a period of time. So you have to be mindful and watchful of that. Next slide. Here are some BMP results. Again, go to the citation, and there's many more of these results that you'll see in the literature. Here's some rules of thumb for you. If you had strict carbohydrates, expect 300 to 350 or so liters of methane per kg VS added. Proteins, a good number to sort of get your arms around is 450 to 550. Fats, 800 to 900 or so. Next slide. Here's some more data that you can gain access to. You'll note here there's also different units. Cubic meters of biogas per ton of substrate. Next slide. Gas can also be estimated from the substrate characteristics, just getting some lab numbers and doing calculations. Though the values may differ rather significantly from what you see when you actually subject the bacteria to the substrate. You'll notice on this, way down on the left-hand side, switchgrass, the BMP was significantly different. The biological BMP was significantly different in the calculations. Up here on the right-hand side, you'll see that though there's still a difference, the oil numbers and the various calculated numbers are fairly similar. Next slide. Here are some of the labs that are providing the services. Please come back to the slide later on and contact these folks for services. Next slide. So the take-home message from this brief discussion about methane potential. Stakeholders need reliable gas quantities for decision-making. Budgetary level methane yields are possible employing BMP techniques. Substrate quantities, qualities, and delivery characteristics are important. Multiple test protocols are available. There's published methane yields readily available, and there are certainly qualified laboratories that are available. Next slide. Contact me if you've got more information. If you'd like more information, more discussion on this. Andy, how'd I do with my schedule? keep it under 15 minutes.
You're right in time there, Richard. Thank you very much. That was great.
Thank you.
All right, and on to our second speaker. Trevor Nickel is General Manager at Highmark Biogas, a technology development and commercialization partnership founded on more than a decade of research in soil science, nutrient management, fertilizer management, microbiology, and virology. Highmark maintains an intensive R&D program backed by investments totaling more than $25 million in research facilities, demonstration projects, intellectual property protection, and knowledge acquisition. Its ongoing R&D initiatives focus on improving the commercial application of IMUS technology, enhancing digester productivity, reducing production and operation costs, and optimizing bioproduct yields. Trevor, the floor is yours.
Thank you, Nandi, and thanks everybody for the opportunity to share some of our observations on materials handling in anaerobic digestion. If we go to the next slide, Nandi, I can just give a brief outline of what we'll try to talk about today in the very short period we have together. I'd like to just outline the importance of materials handling in digestion and where that comes into play. I'll talk about something briefly called the ease availability paradox, the importance of matching feedstock with your digestion approach first and equipment selection second. And then we'll break down a feeding system for a digester into receiving, pre-processing, conveyance, and injection. And maybe have a brief discussion about the equipment selection involved in all that. I'll take a moment here to just talk about where we come from on this. More than a decade ago, the founders of our organization, not intended to be an endorsement, just a story, owned a very large feedlot and were approached by well-meaning scientists saying, hey, you have a lot of manure, 500 tons a day. You should be doing something with it that generates value other than just replacing fertilizer. And they thought that was a good idea, and then they turned the question back on the scientists and said, okay, what should we be doing? And 10 years later, we now have a solution for 500 metric tons a day of feedlot manure. And I'll tell you that the key moment of invention in that happened in 2003, where somebody recognized that the challenge in scaling up anaerobic digestion is all about the materials handling selections you make in the pre-processing and receiving parts of the digester. So if you make the appropriate selections, you can definitely construct facilities and operate facilities that work very, very well. If we go to the next slide, we'll talk about where materials handling happens in digestion. At the bottom of this slide, I've just put a very basic block flow diagram of a generalized anaerobic digester where we have feedstock coming in from the left through receiving, through pre-processing, through conveyance and injection into digestion, and then after digestion through post-digestion processing. All of the boxes with yellow borders on them are areas where materials handling is critically important for function. I'm going to focus most of my comments in this talk on the green colored boxes, so receiving, pre-processing, conveyance, and injection. And it may come as a surprise that we can break this down into this many steps on a generalized block flow, and even more steps when we get into actual engineering design of a facility, given that this is often a pit or a hole in the ground, or even worse, just a tipping floor. The actual conception and design of this is a major consideration in the design and operations of an anaerobic digestion facility. If we go to the next slide, with that in mind, this is the ease availability paradox. Simply put, a given material is much more abundant and available if it is more difficult to handle, especially from the perspective of an anaerobic digestion operator. If nobody else wants it, it's likely to be the stuff that's both cost-effective and easy to acquire. That means we have to design our facilities and operate our facilities in order to handle that available material. Next slide, please. handling that available material means you need to first select an appropriate approach, and then once that approach matches with your available material, select the appropriate equipment to get that material in a form that will be most effective in the approach. And here's some lessons learned, I would say, from observations around our industry and our own challenges over the years. It's all too common in our industry to mismatch the approach and the feedstock. Some of that is just by virtue of the fact that we're a fairly nascent industry with relatively few vendors, and those vendors we generally have one or two or a constrained number of approaches available to sell to customers, and customers generally capital constrained, of course. We have seen a much too high failure rate in installed anaerobic digestion plants in our industry, and part of what we would love to see with the American Biogas Council's assistance is moving towards a much lower failure rate. So in terms of best practices, when scoping a project, assess first the feedstock supply and available approaches that match that feedstock. Now, Richard's given us a really good background on what feedstock is. So when we go to the next slide, you'll see that it's no surprise that your first question is what's in your feedstock. How much of it is water? How much of it is solid? How much of those solids are organic material? How much of those organic solids are recalcitrant? And how much of those solids are inorganic material, things that will cause problems and wear in the digester, whether or not they're small particles such as sand and gravel, or larger particles such as wrenches and boulders and tractor parts and cattle skulls. On the right-hand portion of this slide, there are two substrates pictured there. Both of those have the same water content, and so the same solids content, and the same volatile solids content, and yet they're completely different materials handling challenges. The top picture is very nice, homogeneous, generally homogeneous dairy manure, and the bottom picture is very heterogeneous vegetable waste feedstock. Just so happens that both of these are targeted for the same facility, but have very different materials handling questions around them. And some of these questions fall out not only of the nature of the feedstock, the physical characteristics of it in terms of solids content and organic content, and also the particle size distribution, whether or not those particles are generally homogeneous or generally heterogeneous. And it's almost worth making very broad categories on this, is because all of our substrates are generally heterogeneous, but moving that category limits out. Do you have materials that will concretize due to their heterogeneity? And that's an important consideration. So materials such as silty materials that occur in sand-bedded dairies, silt and sand, and gravel will form a concrete if you leave them long enough, and that's a very important consideration in the feeding system. And then we have the question of viscosity. Is this material Newtonian or non-Newtonian? So like ketchup or like cornstarch, will it thicken when we attempt to move it, or thin when we attempt to move it? And will it bridge and cause issues with screening? These are the major questions. Now we can talk about some solutions on the next slide. The very most common approaches for some types of feedstock involve, for very liquid feedstocks, we see some lagoon digesters. For lower solids feedstock, we see lagoons and some high rate digesters. Sometimes we see some plug flows and CSTRs, the way that we would see in low solids digestion. When I say CSTR, that's a fully mixed digester. For more solid type materials, we see other types of CSTRs, some modified plug flow digesters, and you can see the spectrum goes all the way up to material that's extremely solid, and that goes along with extremely difficult to handle, and you see different approaches for that. Now you can move 1 or 2 steps up or down this spectrum. So were you to have a 14% total solids dairy manure, it's entirely possible with appropriate pre-processing to go 2 steps down and use that in a mixed lagoon, say, or to go 2 steps up and use that in a dry fermenter. But both of those would require pre-processing, and pre-processing is expensive. So as you move further away from the appropriate approach, you add cost and complexity to the system. This is why we say that matching feedstock with approach first is critically important for your materials handling selection, and then matching with your equipment second. If we go to the next slide, you'll see a lovely picture of feedlot manure at the top right corner. That is a materials handling challenge right there. If anybody wants to know more about that, feel free to contact me. Your feeding systems generally vary with approach, but they combine the steps that we've talked about at the beginning of this presentation. So receiving, pre-processing, conveyance, and injection. And like I mentioned just a minute ago, if extensive pre-processing is required, it may be that the approach does not match the feedstock, and going back to the drawing board, broadening the selection of approach is often a good exercise, especially if you're in the early stages of developing a project. If the approach and the feeding system does match the feedstock, then you can get a very, very high level of reliability in your facility. If it doesn't, by contrast, the feeding system becomes the point of failure, or the point of lowest reliability. I think we've all heard of or seen examples of digesters installed or operating where the feeding system is the major headache. And not all of that is equipment selection. Some of that was simply approach selection that could have been thought through a little bit differently. If we break down the feeding system, and we'll go to the next slide, into a receiving system to begin with, you'll note that if we look at the feedstocks along the same types of categories we talked about when we talked about approaches, your receiving systems are generally set up to handle that degree of total solids level. So a liquid often is a directly injected system. So a wastewater digester is often injected directly into the digester. It may be a consideration or a recommendation to consider a surge tank in those for very good reasons. For a very low solids digester, it's usually direct injected, and sometimes with a surge tank. For low solids digestion, you generally see a receiving pit, sometimes open, or a closed tank. Very good practice, and needs to have a pit with some sort of mixing to keep the material from stratifying during the time that it's in the in-feed system or in the receiving system. Similar for medium, thicker substrates coming in a receiving pit or tank, or a specially designed hopper. Sometimes as you get into higher and higher solids material, you'll see tipping floors being employed and multiple steps. So a tipping floor and a specialized hopper and a specialized screening system, and potentially a receiving tank or pit following on from that. In terms of most appropriate material, as you go down this list, things get more expensive. So you're not, in selecting a receiving system, you want to select only the system that you're going to need for the projected feedstock for the facility. As an example, it's probably inappropriate to use a specially designed hopper when you are going to take in only wastewater, and vice versa. Going to the next slide, we can talk about pre-processing, and I know Tom's going to talk a little bit about pre-processing later, but there's a couple main categories of pre-processing where materials handling is a critical concern. I'm not really going to talk about tempering, where we add water or add heat and in some cases remove water. That's fairly typical practice, and I think most everybody and every system does some form of tempering or other, especially when it comes to temperature management. We'll talk a little bit about pre-digestion. There are several methods of enhancing the hydrolysis, so the first step of anaerobic digestion, through materials handling in either mechanical or biological and sometimes thermal methods. So pre-composting makes use of natural biological action. You can pile up your substrate and allow bacteria to attack it for a period of time, which can enhance the digestibility of that. It can also enhance the materials handling suitability of that. So every time you pre-process, you can think of it as moving it towards the more liquid end of the spectrum, and in many cases moving it towards the more homogeneous end of the spectrum. Ensiling is similar. It removes some of the material structure, but also makes it through mechanical chopping and preparation, and then the biological process that happens in ensiling makes the material much less viscous when added into water. There are also approaches where you use thermal hydrolysis or mechanical hydrolysis, pulping, that sort of thing, to enhance the digestion characteristics of the material, and those also tend to move things up the ladder in terms of simplicity of the remainder of the in-feed system. Now, none of those are free to use. They generally involve both time and equipment money in the process. There's a number of determinants when you use those and other pre-processing steps just to handle the material as to whether or not you need to. So if your material is very, very high viscosity, so high that it affects the pumpability and the mixing, this viscosity can be reduced with pre-processing, and I mentioned ensiling and other biological pre-processing as a way of reducing viscosity. There's also some mechanical ways to reduce viscosity. If your particle size distribution is too varied, or you have some very, very large particles, pre-processing it is often used both to remove, but if you want to use them, to reduce the particle size. I talked a little bit about pulping earlier, but sometimes it's as simple as maceration or milling to reduce the particle size. If you're digesting an energy crop, such as hay or switchgrass, you definitely need to chop it, and this is an area that falls under particle size distribution. And then further on, if you have a large amount of contamination, so inorganic materials such as your sand and gravel, tractor parts and wrenches, this contamination is an area where you have to put a lot of effort into pre-processing. You can talk, many can ask questions about contamination and how we get contamination out. Combinations of screening, of mixing, of specially designed hoppers, all very expensive approaches to remove contamination in the feeding portion of the digester. But if you want your equipment in the digester to last any period of time, very important. Moving on, the more simple part of the feeding system. So the next slide talks about conveyance. Obviously, if you're conveying liquids, you can use a water-tight pump, but as you move up the viscosity and thickness spectrum there, you need more and more specialized pumps. Your water-tight pump is not likely to be able to move a 14% total solids dairy manure, so a special pump type must be selected, whether or not that's a progressive cavity pump, or in some cases for very high solids, you're looking at very special pumps such as are used in the concrete industry. piston pumps, that sort of thing. Generally speaking, as you get to the higher end of the spectrum, the material is only pumpable with extensive pre-processing. So you start seeing belts and walking floors and moving floors and augers and screws as the conveyance items, to the point where you can get that material either injected into a digester or mixed with water so that it can be tempered and pumpable. In almost all these cases, the more moving parts you have in your conveyance system, the more susceptible it is to the inorganics in the substrate, and the more wear and tear that they will be susceptible to. So the less moving parts, the better. And I haven't written this down, but I think it's very important to consider that gravity is your best friend when conveyance is under consideration. So if it's possible to move your material under the assistance of gravity, it's very important to do that. Now, the caveat to gravity is that these non-Newtonian fluids often need certain velocities to flow properly down the pipes and lines that they are being asked to flow down. So gravity in and of itself isn't necessarily always the only solution. Moving to the next slide, the last stage of the feeding system is injection. That's simply put, that's getting the material squirted in or dropped in or dumped into the active digester. So obviously once it's pumpable, injection is relatively easy. The only consideration is, can you pump against the head pressure that's available there, or if you're using gravity, do you have the line velocity to get it into the material? If you are using a pump, how many pumps do you have, or is your pump a very reliable one? Oftentimes when we see systems operating intermittently, it's because they have only one pump to do all the work in the system, and when that pumps down, the entire system can't function. So the question of reliability and consideration there. If your material is not pumpable, like in some very high solid situations, injection is quite a bit more challenging. So you have to consider both the distribution of the materials once it gets inside the digester, things you don't necessarily have to consider when you're pumping a liquid into a digester, as well as the spacing between the material when it gets into the digester. And this is especially important in a dry fermentation or dry digestion type situation. Does the feed system match the requirements of spacing, porosity, that sort of things? And you also have to consider the biogas fugitives. And I know we've all seen these wonderful designs where the material is fed into a garage type system with a front end loader. That's a very high reliability feeding system. But all of the design considerations then have to go around how you manage avoiding fugitive emissions and the safety considerations that are around that. This brings me to my conclusion slide, which is the last slide here. In conclusion, although I'm sure we wanted to talk about very specific pumps and conveyors and augers, there's no one-size-fits-all solution for anaerobic digestion feedstock. However, there's good news, and there's a great many approaches that are out there, some more or less suitable for certain types of material. But when you consider all the approaches and look at both the approach and the available pre-processing, suitable pre-processing steps that can be taken, we feel that there is a digestion solution for all types of material, and it's simply a matter of having the wherewithal to select both the best approach and the best feeding system equipment. And we're here to help, of course, is the free advertisement there, but so is every other anaerobic digestion technology provider in the industry. I can guarantee you that nobody wants to see a failed digester on the basis of a feeding system that can't handle the feedstock that it's being asked to handle. So the next slide is just my contact information if anybody wants to get a hold of Highmark. We're very easy to get a hold of, and I'm looking forward to answering your questions.
All right, great. Great. Thanks very much, Trevor. That is very informative. Our last speaker is Tom Ferencevich. Tom is a founding partner and Vice President of Technical Services for Yield Energy. He has had extensive biogas plant operational training on multiple technology platforms, utilizing a variety of substrates from agricultural to urban organic waste. Tom delivers biological remediation and operational support services to existing underperforming biogas plants across North America. His work also involves consultations to the financial industry and project developers of renewable energy projects. He has given biogas technology courses for the Composting Council of Canada, Ontario Waste Management Association, and various gas and electrical utilities, and has presented at numerous renewable energy conferences in Canada and the US. Tom, over to you.
Great, Nandy. Thank you very much. So just thank you for my other presenters for handing off. I think my presentation is about I guess feeding control, and it does a little bit straddle Richard and Trevor's comments, but then takes it in a direction where we're really considering sort of the bacteria in the equation. So just a quick comment about yield. So as the other presenters really talked a lot about manure and let's say agricultural organic feedstocks. Yield energy, we're focused largely on urban organics and dealing with like depackaging and things like that. So when we're talking about feed control, we're talking about a number of different aspects, not only the biochemical, but sometimes the physical aspects of dealing with the feedstock and looking at the different, I guess, the constituent components of that feedstock. So really okay, next slide. So when we're looking into feed control, we're really sort of looking at two major industry I guess developments recently. So one of them is co-digestion, and the other one is depackaging. So in order to discuss feeding the digesters, we have to really look at what's your feedstock, and we all know that really everything it's all about feedstock, and knowing a lot about it. And the mistakes that we've seen in the industry really come to just a lack of digging into enough details on the front end of a biogas plant. So, and our perspective is that really it's critical to differentiate what's important to the bacteria and what's important for the system design and process controls, which is really kind of the design and engineering part of a biogas plant. The way I would break this down is looking at both the physical and biochemical characteristics of your feedstock. And physical meaning plastic, sand, grit, metal, glass, and how to deal with those, and also the biochemical characteristics, which, as you'll see later in some slides, is really the carbohydrates, fat, and protein. Those terms lumped together are considered the organic solids or the volatile solids. And then the impact the second point is discussing sort of the impact on system design and operation. And again, that sort of partly what Trevor was bringing up in the fact that your pre-treatment systems and how you're actually going to feed the digester can have a material impact on what happens, how you're going to control that amount of substrate you're going to put in the digester, and ultimately, what that's going to look like physically and biologically for the bacteria, which are the guys that have to do the work to make your money. Next slide, please. So what are we talking about physical parameters? So what we're talking about is conditioning and pre-treatment of your feedstocks, and we're talking about, and this is actually required for both agriculture and urban organics. So we're looking at, agricultural. It doesn't necessarily mean clean, and our kind of point is that, there's no such thing as clean feedstock. And of course, when you get to urban organic waste streams, there's definitely no such thing as clean feedstock. Anytime we're dealing with people and separation and source separation is great, but things ultimately aren't clean. So the next part of it is, so it's really because of this we need to understand those two components can be combined or described as digestible and non-digestible fraction of your substrates. And also in part of this, we need to consider what I would we look at from an engineering perspective is the energy balance of a plant. So when you look at what you're trying to accomplish in getting the right thing to your bacteria, what is the energy balance going to look like? And to keep in mind that the old saying of if it sounds too good to be true, then that's the case, and our experience is that is reality. So things have to add up in a digester. What goes in must come out. Nothing can be created new or destroyed. There's the net flows of water and energy and everything have to equal 100%. So really look at it from that perspective, and you can do high level looking at it and just do simple things like how much water and substrate goes in, and how much energy goes in, and how much am I getting out. Those are really kind of good metrics to measure this, whether things are going to add up in your, I guess, the approach that you might be considering. Next slide, please. So I'll go, Trevor touched on this, so I'll just go briefly about it. So this slide really talks about clean substrate feeding and pre-treatment, and there's different things you can do. You can chop things, you can mill them, you can grind them, and my comment on all these things are just consider that when you do this material, is this the only thing that's going to go in your digester? We're really in this part where we're talking about agricultural feedstocks, and maybe you can feed this completely dry into your system, but maybe you don't. Maybe you have to mix water into it, and so it's just to consider that certain feedstocks, again, just to match to the right type of pretreatment. And really, when it comes to this substrate, usually it is what it is, and there's not too much. You can predict ahead of time with some relative confidence whether you're going to be adding anything extra like water in your process. Next slide, please. So when we talk about, back one, please. Yeah, thank you. When we talk about removing physical impurities, so now we're talking about urban organics, or what I would call dirty substrate, or things that have physical impurities. You can't just put things into a digester for your bacteria, right? So you have to actually do some things to it, and we're talking about particle size reduction, and we're talking about separating packaging from the organics, and packaging could be from a store, or it could be from people putting things in a bag in a municipal organics environment. So the typical equipment used in the industry is just shredders, screw presses, press type pumps, hammer mills. And all of these things require both a special know-how. They also all come with their own set of operating parameters, both from a time perspective and a manual, changing things, but also from a water balance standpoint. So really, what we're talking about here is, the whole point about substrate pretreatment when it comes to urban organics, it's all about density differences, and how are you going to actually separate your contaminated material from the packaging. Next slide, please. So there's, in this scenario, there's two paths you can go on. You can either go the high water use path, or you can go on a low water use path. And this is the way I would characterize, looking at the equipment or systems for pre-treating and feeding urban organic waste. And so why are we talking about all this, right? So we're saying the point of all this is that your water balance influences your how much food per cubic meter per ton you're going to be feeding a digester. So for example, if your equipment requires 1-to-1 water to substrate ratio, then you put 1 ton of feedstock in, and you're putting 1 ton of water in to clean the substrate, then you're reducing your organic load by half, right? So you're handling more, but your organic loading rate inside your digester is actually lower. So these are sort of just at a high level, looking at some of the number games that can come out of dealing with different types of feedstock and different types of equipment and processes as you're considering your feedstock. And again, you need to know your feedstock, right? So you need to know their characteristics. You need to really know about the contaminant fraction. You need to pay attention to these things and try to characterize them as best you can, because they're going to greatly influence how what your approach is going to be, and ultimately some of the sort of scientific parameters around all this in terms of your biological stability profile inside your digester. Next slide, please. Okay, so what are the impacts on the system of sort of choosing different technologies to deal with this? So the science and engineering of separation, as I mentioned, is based on density of differences. So depending on if you're looking at a retrofit case or is it a greenfield operation, you know, if you're using more water, it could mean a lower retention time, or it might mean you need larger tank sizes, and so therefore you're going to, maybe it's going to change your capital cost for the situation. Generally speaking, when you're looking at screen sizes for screening out and filtering plastics and metal and glass, and specifically with urban organic waste, you're looking at, you know, the smaller the screen sizes, you get more organics separated and you require higher water usage. Larger screen sizes, you use less water, but then you're also letting more, potentially more packaging and that contaminant fraction through as well. Also remember, with a smaller screen size, sometimes you're actually, not so much is important as how much contaminants you're separating, but really how much organics you're actually separating with smaller screen sizes. So then this relates to an energy balance and why you really get you actually get the gas out of your system. You might be actually separating more organics than you realize from your system that you're not feeding to the bacteria. Next slide, please. So just quickly, we at Yield, we advocate multiple steps, phases in pre-treatment and cleaning stuff. So we, you know, no single piece of equipment can clean organic waste enough to prevent downstream problems. Usually it's best to take a systems approach. Suspension slurries can create, well, they can be contaminant and they can contain heavy amounts of, a lot of heavy fraction. It's sort of the hard part. Like plastics in that, you know, you mostly get them. Sometimes they make it through different systems, but they're the hard ones to get out are the heavy material in a single step, let's say. You also want to achieve particle size reductions, so you're getting smaller things. Bacteria don't have large teeth, so they can't eat substrate very well, and they don't like to move, so they like to have food get to them. So this is, you know, an important point. And again, heating during the pre-treatment process will also help in contaminant separation. Next slide, please. So now we're looking at, so now we're just going to get into some of the biochemical parameters. So ADs have suspended bacterial growth. So now we talked about, you know, some of the parameters at the beginning. You've got your organic material, which contains a fraction of water. It contains mineral ash component, and it contains some contaminants, whether it's light plastics or heavy plastics. So now you're going to get all this material. It's going to go into the digester. Now what happens? So you've got your suspended bacterial growth. You're trying to destroy all those volatile solid compounds, produce gas, and again, just so we're all clear that, you know, the main food, you can only get energy from carbohydrates, fat, and protein. You can't get energy from water. You can't get energy from the grit material. You can't get energy from plastics, and you don't get energy from ash. So it's this is the component that you need to consider when you're feeding your digester and you're maintaining optimal operating parameters. Next slide, please. So we've probably all seen a slide similar to this. This is the sort of the anaerobic food chain, and again, so as we just illustrated the point before, that it's the carbs, fats, and proteins that are really the food for the system that generates our revenue in terms of gas production. And out of all these steps, the two most critical are the degradation of propionic acid, which is the sort of the third stage there, and this acetate degradation and methane formation, which is the fourth stage. So those are your rate limiting. So when you're talking about controlling your feeding and looking at, you know, what are the constituent components, the results of these digestion of these carbohydrates, fats, and proteins, you know, the first middle stages there are relatively stable and happen consistently, and it's really the last stages there that are the rate limiting in the process. Next slide, please. So here's a chart, a little bit about, so what do we get out of carbohydrates, fats, and proteins? So here's the relative contributions of gas, of biogas, from each of these substrates. So carbohydrates, you know, 50-50 of methane and CO2. Fats, 70. As you can see, fats generate generally more energy from fats. You get quite a lot of energy from protein, but as you look across, proteins are also problematic because they add your ammonia and your H2S. So when you're looking at feeding control, it's the proteins that really are often, you're looking at co-digestion, and you're looking at different, whether it be, could be clean material from slaughterhouses or high fat and protein content material, and your organic load is much higher. It's the food is rich. It's like like you're giving a cheesecake to some bacteria, or a cheesecake to us, and it's very rich. Next slide, please. So in terms of defining and discussing these things, organic solids are equal to volatile solids, which is which is the same. These terminology can get confusing sometimes, but these are basically referring to the things that can be digested. Your organic load is the load in kilograms per cubic meter of digestion volume per day. And again, as I mentioned, all those organics contain a digestible and non-digestible fraction. And you have to include these into your into your mass balance, because even though they're not going to generate you revenue, they impact how you're feeding your digester. They impact really how much food you're going to be able to get, and that's related to two parameters, which is your retention time and your bacterial doubling rates, which are really related to how much food you can safely digest in how much you can load in the digester at any given day. Next slide, please. So here, I've just outlined here sort of the classical case of organic overloading. So generally, this happens there's a couple of feedback loops that here happen. So this is just a sort of high-level look at what really happens when when you get an overload situation. So when you've given too much food to your bacteria, the digester can't handle it. You've got a situation where you've got a given volume, and there's just too much food for the bacteria to be able to digest safely, and so you get a buildup of metabolites. So when we talk about like a working velocity, so we talk about the rate of those reactions I showed you in the previous slide, stage 1, 2, 3, 4. Those things have to happen. When they all happen nicely and everything is working its way through, then your digester works really well. When things start to go wrong, the typical case is you get, and this is just sort of too much food for the bacteria to be able to digest in the time that in the retention time you've given them. So you get increase in hydrolysis and acidification. So then the next thing that happens is the methane concentration starts to decrease and CO2 rises. There's some other feedback loops that happen here in terms of CO2 solubility. The organic acid accumulation overwhelms the buffer capacity. So you get acidification, and the buffer capability to the system's buffer, the carbonate buffer system and the ammonia buffer system can't work anymore. They're overwhelmed. You get inhibition of acetogenic and methanogenic bacteria at this point, so hydrogen can't be passed on this pathway any longer. So then which also contributes to a buildup, and then you get your pH value begins to decrease, and as soon as you get it goes below less than 6.5, your pH or digester will die. So this is sort of the classic case. Nothing sort of strange going on here, or like toxicity from another, an antibiotic, or you have a dissolved nitrogen problem or anything. This is sort of just too much food. Next slide, please. So, as I mentioned, so just a summary of that, your organic loading rate is very high when this happens. You get maybe it's insufficient retention time, so you haven't sized your digester properly. For what you've intended on feeding them. Number of reasons, sometimes this can happen. We see it, if somebody decides to take a load of something, a feedstock, that's great. It pays well for a tipping fee, but really their digester can't handle it. I've seen this a lot in cases where, again, co-digestion is really where our industry, I think, in North America is at, and so you're looking at the tipping fees coming with material, and so it's sometimes hard for owners or operators to turn away something that's going to pay them, but ultimately it may not pay if you've got downtime related to an organic overload and an upset, because you have to calculate your revenue losses from your downtime, plus the fact that you can't take any more of this material, so you've lost tipping fee as well. So doing some good calculations on how you're going to feed this material. And remember that it's your bacteria that are your rate-limiting reactions to all of this. Next slide, please. Okay, so this is sort of last slide here, and we're just to summarize that your feeding rate and how you feed your digesters is not just it's not linear. It's actually a combination of things, right? It's a combination of the energy generating component of how much carbohydrate, fat, and proteins in a cubic meter of material you want to feed the digester. What the physical attributes of that material is, and really what I'm talking about there is I'm saying how much water you're going to use. Are you going to want to use no water, or do you have to use a lot of water? And that will affect, on a per cubic meter basis, how much energy is going in the digester, whether you're diluting it unnecessarily. And that's really where it comes to. You can always, water's not harmful, it's dilution. So, you really have to look at, well, am I handling and processing the water? Where do I have to truck it? So there's other costs associated with handling water. In and of itself, other than potentially making too low a retention time of the water in and of itself doesn't harm a digester, but it can cost you money for use and disposal, and then the water balance. So yeah, really, what are you looking at for equipment? Does this match up with your system design? And how are these things all going to interact once I put them in the digester? Digesters operate at no higher than a 12% total solids, really. For generally, we're looking at, we're not looking at, digesting energy crops in the European market. And under those, CSTR type of digesters, we have to realize that, you're putting in 2% per day of your daily feed, and you're operating anywhere from 6% total solids to 12% total solids. So you have to, you have to match all those operating conditions. That's the conditions the bacteria they're optimal at, and they do their best work. And so these are just things you need to consider when you're making your system design and operating parameters. And that's the end of my presentation. Thank you. Mandy?
Yeah, Tom, thank you very much. That was great. That was great. And that concludes the presentation portion of the webinar. We will now begin Q&A. I think all three presentations really delved into the topic at a really high level of detail and are really highly informative. So informative, in fact, actually, that we only have one and only one question. So panelists, to know in particular, anaerobic digestion increases the formation of struvite in effluents. What is recommended to avoid this effect? So, Trevor?
Anybody want to have a crack at that? So
yeah.
we focus most of our presentations on the in-feed system, but the questioner is correct that in certain situations you can generate struvite through the process of digestion and end up with that either being problematic or positive in the digestion effluent, so to speak. I think the question was, can you limit or avoid the production of struvite? The answer is yes, unless that's an inherent quality of the combination of feedstocks that are being processed. Generally speaking, it's an excess of magnesium ions that allows the formation of struvite in the digester. And if there's a particular feedstock component that's high in magnesium, that could potentially be removed and limit the production of struvite. On the other hand, if it's not causing problems in coating pumps and pipes and heat exchangers, formation of struvite, and especially coming out in the effluent, may in fact enhance the value, agricultural value, and potential sales value of the effluent. Does that cover the basis?
Yeah, I could add a comment just on our food waste systems that we do. We haven't had any problems with struvite. So.
All right, great. Thank you. Thank you, Trevor and Tom. We have another question that just came in. Have you seen digestion of horse manure with a 80-20 ratio of straw manure? Can you grind this up, and how?
So digestion of horse manure, very possible. I'm not sure if the question is with bedding straw on top of the horse manure or just the horse manure itself with a large amount of straw inherent to the product. I can address both of them quickly. Horse manure of itself is well processed through the digestion system and the chewing of the horse, and is a fairly good substrate. Might require some tempering for digestion. Depending on the digestion approach, it can have some very good yield, and of course depending on what was being fed to the horse at the time. Now if you're talking about adding considerable amounts of bedding to it and straw, you start getting into a situation where pre-processing is highly desirable. Straw is problematic not so much in the feeding system. It does increase the viscosity considerably of the material you're trying to pump or convey into the digester, but it does also contribute to an effect called stratification in the digester, where the straw particles will catch rising bubbles of biogas and get driven up to the upper level of the digester, and in situations where the digester is not designed specifically to get around that problem through enhanced mixing and mixing zones and that sort of thing, can be very problematic for digester operations. So very desirable to pre-process high amounts of straw in a feedstock.
All right, great. Thanks, Trevor. Another question that's come in, what do you recommend to control odor?
Sorry, was that to control odor?
Correct, yes.
Yeah, odor. Well, you know, from my perspective, and I mean, Trevor, you can comment as well. Like there's many points of odor in a biogas plant, right? So you can, if you're looking at a pre-processing system, when we deal with, when we design a facility, let's say 25,000 ton facility that's with urban or all food waste, 100% food waste. You know, we have it's the building design, right, and it's air handling. So we have biofilters generally are used to you know, reduce the odor. Some other things that we do, we have our pasteurizer is not a batch pasteurizer. It's a double tubed heat exchanger with continuous flow. So we're not having a lot of air discharge from pasteurizing systems. We have a receiving bunker. We don't tip our organics onto a floor. It's all about neat and tidy and keeping things, again, for us, we've specifically addressed stuff by putting more things in piping, strong pumps. We use piston press pumps in our systems. So not too many points of open air, as little as possible, and everything's covered and sealed. The building is under negative pressure, and those are standard industry best management practices.
Absolutely, thanks, Tom. That's a very comprehensive list. The other things I would add to that is where you're storing effluent liquids. Generally speaking, it's a good idea to put a cover on top of it. And there are some techniques to even kind of trap the ammonia in the effluent. So that's one source of odor. The other thing that I've encountered around the world when visiting digestion facilities is there's often a small amount of biogas venting, and often, I alluded to this in my presentation, often that's coming from the in-feed system, though sometimes coming from a flare system that's malfunctioning. And it's very important to draw that biogas back in, either through a biofilter, as Tom mentioned, or into the flare system.
Great, thank you both. I see some questions coming in regarding BMP testing. These would probably be directed at Richard. Unfortunately, Richard had to drop off from the webinar, but he is welcoming any questions that you may have by email or phone. I'll make both of these pieces of information available to you. There'll be a slide coming up shortly, and they'll be made available to you as we send out the slides. So those are the only questions that have come in. So thank you very much for your questions, and thank you, panelists, for addressing them.
Thanks, everybody, for your questions.
All right. So before I close, I just want to note that we will make available this webinar by Monday, August 20th at the very latest. We'll get a recording of the webinar and some slides to you. Just to note some upcoming events, if you haven't done so already, please register for the next webinars in our series. The next one coming up will be on safety on August 30th. And the last one will be on operation and maintenance coming up on September 27th. Also coming up, we will be having a workshop at the Biogas USA West Conference in San Francisco on October 9th. That will focus on developing the biomethane to vehicle fuel market. We'll also have a workshop at the RETEC conference here in DC on October 16th, focusing on waste to energy. So stay tuned for more details from us about those events, both on our website and through our newsletter. You can sign up for our newsletter at americanbiogascouncil.org. Please don't forget to fill out our survey. I highly implore you to do so. Your input is valuable to us and helps us to improve our webinars. You can sign up to receive biogas news on our website, as I mentioned a couple of moments ago. And please do consider becoming a member of the ABC. You'll receive frequent policy and market intelligence updates. You'll have access to opportunities for business development and networking with key biogas leaders. And this is your chance to help shape the biogas industry. So here's the information for each of our speakers. This will be made available to you early next week. And with that, on behalf of the chairman, Paul Green, and our executive director, Patrick Surface, I'd like to say thank you to our panelists. Thank you, Richard, Trevor, and Tom. Thank you to all of our attendees for joining us today. And if you want to learn more about the biogas industry, ABC, or membership, visit americanbiogascouncil.org. Thank you, everyone.